Okay, first thing, I want you guys to define these terms, and we're going to actually get a rigorous version of these definitions throughout the lesson, but I want you to make an attempt first on your own and see how much you know. Give it a second, pause the video, and then come back to it when you're done. All right, now, first thing we want to do is we want to take a brief glance at the parent functions. Want to make sure that we remember these are usually the basis for algebra functions that you will work with, although there are outliers, there are whole other sections that you will see that follow the same principles we're learning today. It's just that this is a good foundation. Okay, and even though we'll be using some of them today and not all, the principles will apply to all of these parent functions. You should have this chart in your notes. Okay, first thing I want to do is we're going to explore how to use these values in the functions and what they do to the graph. They are what define all of our transformations. So we're going to work through A first. I'm going to take this slider that will change the value of A in this function. Now, if you saw in that chart of parent functions, this looks like the first one. It's linear. We're going to work with this linear parent function and we're going to adjust it. First thing I want to do is I want to make A, so if I can move A from -10 to 10, that's a pretty good range because it starts at 1. If I go to 0, I've got no graph. I've got a graph, but it's not something that can really show me anything. So I want to start at 1 and I want to increase it. So when A increases, this graph looks like it's stretching away from that x-axis, from that 0 graph. Okay? And so that's important for us to note. And in fact, in your notes, in these materials, we've got this here. So I'm going to write that down. Okay, got that in the notes. When A is greater than 1, the graph stretches these ends away from the x-axis. Now we're going to go back, and we're going to try making A, let's go less than 1. Well, suddenly, instead of increasing away, those ends of this graph are starting to lean towards the x-axis. Okay, so let's put that in our notes. Okay, so I'll give you a second to write this down. I actually made the definitions a little bit nicer. They looked a little wordy before. And I'm using the term stretches and compresses. So remember, stretches is whenever it's becoming a steeper graph, and it compresses whenever it's becoming more flat because it's approaching the x-axis. All right, now let's talk about, we got when A is between 0 and 1 and when it's greater than 1, but we don't have when it's less than 0. So let's go to less than 0. Oh, look at that. It's suddenly like it's flipped. So if I go to -1 instead of 1, that's exactly what's happened. My graph has flipped. So I want to put that in my notes about what happens when A is negative. If you'll notice, the behavior, the stretching and compressing, it still happens. It's just it's now on the opposite side of the x-axis. Okay, so I want to put that in my note. If you'll notice, these notes that we have here, they all relate to how the graph relates to the x-axis. It's very important to notice its behavior, the end behavior towards that. Okay, so we'll do the same principles for H and K, but let's actually go look at some other types of graphs, like the quadratic, to see if there's a difference in how A behaves here. So I've got A at 1, just like before, and the first thing I'm going to do, just like these notes that we have here, is I'm going to talk about when A is greater than 1. So I'm going to make A greater. If you'll notice, what do you think is happening? When you look at this, what do you see happening with these ends of the graph? How are they moving in relationship to the x-axis? Those ends are they, so when A is greater than 1, they're getting further away. In fact, not just greater than 1, when A is increasing greater than 1, those ends are stretching away from the x-axis. Well, I think that's actually what I have in these notes. When A is greater than 1, the graph stretches away from the x-axis. Well, that looks pretty good. I'm actually just going to copy that so I can put it in these notes. Looks good. Oops. Okay, next I want to do the same thing that we talked about last time. We did greater than 1, and then we did between 0 and 1. Well, let's look at what happens when it's 0. Exactly the same thing as the linear function, or parent function. When A is 0, there is just a horizontal line at the x-axis. It doesn't do anything. So I want to go, well, look at this. When I have those decimals like before, my graph looks like it's getting closer. So here's the standard. It gets closer to the x-axis. So it's being compressed toward the x-axis. I think that's what I had in the notes before. When A is between 0 and 1, the graph compresses towards the x-axis. Looks good. I want to copy this too. If I don't have to type it, I don't want to, because I'm lazy. Just kidding, because it's efficient. All right, and then the last thing we want to talk about is what happens to our graph when A goes below 0, when A is less than 0 or negative. So I'm going to make my A negative. There it goes. Same thing. It's flipped. And let's see, does my end behavior work the same? There's -1, so I make the numbers, the absolute value of these numbers greater. And look at that. It's stretching away from the x-axis. And when I'm going with my decimals, it's getting compressed towards the x-axis. So this looks to me like those notes will work again. So what I want to do is I want to note nothing changed in the A for the quadratic and the A for the linear. Those are the same. It serves the same function. Okay, let me go back and get those notes. When A is less than 0, the graph flips across the x-axis. Control. Alright, I want to paste that into here. I now have my notes for A for both of these. Same thing. And let's go look at the A for one more type of graph. This here is an exponential. If you'll notice there's a 2. If you go back to the parent function of an exponential, sometimes you'll see people use a B with their notes, but 2 is just kind of where we start off. So we're starting off with a 2, but we're still going to work with the function the same way. Okay, let's see, it's got this. H and K are listed at 1 right now, but that's just because otherwise this would line up with the x-axis, and that's going to be harder to see. So don't worry too much about that. That's just for the sake of seeing the red line. We'll see that when we get through those notes later. So let's change A the same way. It's at 1 right now. Let's increase it. Now this is doing something a little bit different. Not really, but a little bit different because this doesn't look like it's changing. However, now we've got this central curve increasing and we've got the end behavior stretching away from the x-axis again. So even though this may not look very clear to you because of this side, it's still doing the same thing. And we'll talk more about exponential functions later, so we don't need to worry about that too much right now. Just understand that end behavior is performing the same function when A is greater than 1. So I'm going to go back over here, take this. I'm going to put those in my notes for this exponential A. Looks good. And then, oops, sorry. I'm going to do the same thing again where I go between 1. Well, look at that. That end behavior, that end is starting to go, there we go, it goes towards the x-axis. Again, it's just because the H and K are different that it's not actually touching the x-axis, but that's what would happen if A became 0. And oh, look, the same thing. When a is negative, it's flipped over, but it still does the same function. So I'm going to come back over here and just take these notes as well, because a works the same way no matter the function. It will always do these things to the graph. Alright, so that's an introduction to A, and we're going to go ahead and do the same exact things for H and K and see where that gets us. And understand, these are different variables. They're different parts of the graph because they serve a different function. So we may not see the same behavior. So let's go back to the linear, and we're going to do that right now. And this is just a note to the people evaluating this, the committee evaluating this video. Just for the sake of time, I'm going to skip H and K. Those are a little less complicated anyway, so that I can show a little bit more of what I've got. Okay, so assuming that we went over H and K, let's talk about what happens to our graph and what happens to the values of the graph when we're doing these transformations. Specifically, we're doing the expansions and compressions, because at this point I would have already gone through the specific terms, expansion, compressions, and reflections. So let's talk about what happens to our graph when we have, to our values. So I've got the parent function of quadratic here again. It's what you're going to see for a lot of transformations because it's so basic and so easy to look at. And these are the basic values. Again, if you want, I can add another one. Let's go 3. Looks good. And I've actually got a function here with a new value of a. Instead of just the 1, the coefficient of 1, I've got a coefficient of 1/2. So a is 1/2, which is between 0 and 1, which means my notes tell me that my graph will be compressed towards the x-axis. And let's just see the graph. That's what happened. These values were pushed down basically towards the x-axis. And let's look at the x values. The y values. My y was 4, but it changed to a 2. Well, that makes sense, because I would take that 4 and I would multiply it by this coefficient of 1/2 to get a 2. My y value was 1, but it changed to 1/2. Well, 1 times 1/2 was going to get me that value. And then it's not really showing up on the graph because the 3 is so much higher, but my y value is 9, and then if I multiply it by 1/2, that's getting me 4.5. That's where this one's coming from. So I'm shrinking the graph down by 1/2 of the because 1/2 is my a, and that's what's always going to happen. So just one last check, we can see the 2 does the same thing, because my a here is 2. From 4, that would take me to 8. From 1, that would take me to 2. I'm multiplying these values by the coefficient. Now, when other transformations become a part of the process, then it will change the way we look at the graph as well, and we'll look at that in another lesson more clearly. So one more example here. Here's a rational. I've got the parent function graphed. Notice the undefined, that's just a characteristic of it. And then I did the same thing with 1/2 for a and then a 2 for a. Well, this value gets cut down, or all of these values get cut down by 1/2. And then so we're going to assume that our graph is going to be stretched down, be shrunk down or compressed towards the x-axis. That's exactly what I'm seeing here. This value got compressed towards the x-axis, and this one did too, by a factor of 1/2. All of my y values got compressed by that factor. And then really quickly, I've got I had a 1 and they were stretched away by a factor of 2. That's always the case. It does not matter which parent function or which function you're looking at. Thank you very much for your time.